Hi, David Vizard here. You guys are watching PowerTec 10. What we're going to do today is look at Mopar Joe's cam challenge and how my situation fits in with this challenge.
I'm sure most of you all know exactly who this is, and I'm excited that he is conversing with me today about our 538 Big Block Mopar Camshaft Challenge. I really look forward to getting his input on this.
Well, let me just say, for the benefit of your viewers, that I'm very, how shall I say, flattered that you made room in your competition after technically it was closed for me to have a go at this, right? So, and young Daniel, the camshaft company, said he would grind the cam for me at his expense. So I'm kind of indebted to you guys. So thank you very much for that. I very much appreciate that, Joe. I've been meaning to get to the calculations for this, but tell the viewers what it is we're dealing with exactly. Right. All I know is it's a big block Mopar.
So it's kind of an interesting mixture of components here. So we have we start with a stock 440 block, which would be the RB raised deck block. The owner of this car, engine, project, etc., he's got a 72 Plymouth Cuda. He wants this engine. Its design destination is to be a drag and drive car. He was dead set on having a 4.5-inch stroke crankshaft in this engine. We're looking at 4 360 bore. So it's actually more stroke than we have bore size. And I feel like that's going to be a challenge because he wants to turn 6,500 RPM. And
what's the piston speed at that?
I'm honestly not sure. It's a 7,100 rod.
In it.
Yes, sir. Right now we have a Cali's Compstar crankshaft, Molnar rods, yep. And we're looking at, I believe, Wiseco pistons now. So Daniel's ordering our pistons. He has our heads. These are Trick Flow 270 heads that were reported by Charles for video. I know
Charlie, good old Charlie.
Yes, sir. He's a student of yours, I've heard.
He's also a lot of fun to be around.
Yes, sir. He's done extensive work to those and to the intake. So our intake, we have a single plane. It's a 4150 intake. And that's part of our challenge with this is that the owner wants this to fit under his flat hood of this 72 Cuda.
Yep.
So we really can't. We're kind of limited by we can't stack 2-inch spacers. He doesn't have really room for a dominator. I know you and I spoke about that before. And even with testing, maybe we could slip one on, but at the end of the day, it has to run with those constraints.
Can I ask a question here, Joe?
Yes, sir.
Any possibility that we could do our dyno testing on a 4500 carburetor and a spacer? Because that engine is going to, big inches and some good heads. It's going to absolutely suck the innards out of a 4150 carburetor. We'll find parts in the cylinders, right? So what's the chances of doing the testing on a 4500 car?
I'm certain I can find one. I know I have an adapter, like an HVH super sucker adapter that would go for the tapered 4-hole spacer into a 4150. That would be the easy choice of just bolting that on.
Yeah.
Try to go for more.
I would estimate for this engine, we really need something, a minimum of 1250, and I would think 1350 might be nearer it. Right. I mean, I know Charlie's going to do a good job with the head.
Yes, sir.
Right. You've only got one, you've got a problem.
Well, I'll say I have his flow numbers. I think our max flow right now is 371 at 700 lift.
Yeah.
And
well, there's enough power potential there for it to pretty much demand a 4500 series carburetor.
I know the owner is very set on wanting to spin RPM. He wants 6,500 plus. But
well, we'll see. You know, we could work out the piston speed
yes, sir.
with my program. So yeah, you know, as you just pointed out, the piston speed is going to be up there, 6,500 RPM. And what was the stroke again? 4.5.
4.5 inch.
Yeah. I mean, it's possible, but he better have the very best stuff.
Yes, sir.
Right? I mean, I know John Casey has built 4.5 inch stroke engines that he's turned to 8,000, but some of them even more than that. I mean, but John's got the world record for piston speed. Did you know that?
I did not know that.
No, his engines have more piston speed than even the highest RPM Formula One engines.
Wow.
Right? Yeah, yeah. And they live, but for a drag strip, certainly not a road car and a drag car. So I think your guy is going to be RPM limited. What do we make the cam for? 6,500.
That's the goal. And I would think for our testing, it's going to have so much torque. Typically, and when I dyno test at Kuntz, they have an issue pulling, below 3,800. The dyno just is loaded up. It can't read torque after a certain point because
it's a baby one.
Well, the previous, I think my previous engine there was making over 800 foot-pounds, and it carried it for
well, is it a superflow?
Yes, sir.
Yeah, yeah. When you get to those very big torque numbers, you need 2 absorbers on it. I was lucky when I ran out of capacity on my superflow and I had a special big absorber on it. I had a friend who had an aero dyno. This sucker had a 19-inch absorber compared with the superflow's 5-inch, and the absorber impeller weighed 90 pounds.
Wow.
And it would pull down a pretty big aero engine, making maybe 5,000 foot-pounds down to 1,000 RPM.
Mm-hmm.
I put my big block on it and I could pull it down to stall it. And this was a nearly 2,000 horsepower big block. So it did the job.
I know they've upgraded and built a new room with a new dyno there, and that's what Eric Weingartner's trying to use for his current camshaft challenge. They've had some issues trying to get that dyno to read the computer of the dyno to read the actual meter itself, I believe.
Yeah.
So that's where they're at.
It's another in this business, isn't it?
Yes, sir. They've had the Australian experts over and everything, so it's getting close. Everybody is geared up for it.
Now, I did have a question here. Everybody else has got their entry in, right?
So far, Brian's cam is ground. Daniel is working on his now.
So we really should get mine sorted out, and then you can communicate with him.
Yes, sir.
On there. Well, okay. So what I'm going to do here is use the configuration of this engine will be such that I can use my big block Chevy program and just change one of the constants in it, and it should be close.
Yes,
so that's what I'm going to do here. So it's not a program specifically for a Mopar. It's a program for big block, which is incorrect or appears to be, well, no, I know it is. It's incorrect in one area. It's just I've got to determine by how much it's incorrect. So what I'm going to do is that. So what I'm going to do is use my big block Chevy program to calculate what the cam events should be. There's no initial input on the valve events at all. I mean, you'll get some people, they will say, well, I calculate my cam, right? And I start with deciding where I'm going to close the intake valve. Well, you didn't calculate that. You guessed it.
Mm-hmm.
I don't do that. I start with a blank piece of paper and the engine tells me what it wants. I don't tell it. Right? So I know that your experience with the engines and cams you've tested has revealed certain areas of importance which sometimes are overlooked. A lot of people think the most important is the intake valve closure point. And my experience has been that it's not that much, it doesn't give that much influence, which it doesn't, right? For what it's worth, the lobe centerline angle is about 5 times more influential than the intake closure point. In other words, you move the lobe centerline by 2 degrees, and that's equal to about 10, 12 degrees of difference in closure. And you've only moved it 2 degrees. Of course, it varies. If you are dead right and you move it 2 degrees too far advanced, it has almost no effect on the power curve at the top end, but it doesn't idle as well. If you have 2 degrees too retarded, then it can take a chunk of power out everywhere. So it's always better to have it slightly advanced. I found it's always better to have the cam a little more advanced than you think it needs to have, as that doesn't seem to hurt. You've done quite a bit of cam testing here, Joe, or rather testing of engines and fiddling with them.
Yes,
right?
sir.
So what have you found with these Chryslers?
Well, I think the installed intake center line may not have as much effect as some people think. And being off by a few degrees, it could be potentially harmful, but you wouldn't really know until you're on the dyno. Is that what you would gather?
Yeah, but and that's very true. And a lot of times, and here's something that a lot of people don't realize: the nearer your cam is to being right in terms of its opening and closing points and the ratios between us, that's the lobe centerline angle. The nearer the lobe centerline angle is to optimum, the more fussy the timing is. And this is how I explain it to people. If you've got your cam lobe centerline off, say it's too wide, when you advance the cam, the intake function may get better, but the exhaust will get worse, and they kind of cancel each other out. And when you retard it, the exhaust function may get better and the intake worse. So, and I've had people say, well, it doesn't seem to be too fussy about the timing because the power goes up and then it hangs like this and it goes down. Now, if you've got it right, when you advance the cam, both intake and exhaust are wrong. When you retard it, both intake and exhaust are wrong. So now your power curve goes like that. There's the optimum. You've got almost no margin for error. And I'm imagining here with this big engine that what we have here is something where, as good as Charlie is, there's never enough flow.
Right.
So we've got to make use of every single CFM at every part of that opening phase and closing phase and put it in the right place. So getting the cam right on the lobe centerline angle and then timing it in right could be the last 25 horsepower, which you didn't get by. And if the lobe centerline angle is wrong, you could be 50 horsepower off.
Wow.
Yeah. I can give you an example here. I had a cam specially done for me by Comp, some special profiles that Billy had just introduced. So I sent him in a request. I said, Billy, can I have a cam ground like this, with this and this on this lobe center line angle? Right? And he said, sure. Got the cam done. Then I had this guy call me up. I swear he was a beginner there. I think he must have been one of my fans and he wanted to impress me, or impress me that he was a good comp cams guy. And he called up and he said, now, be sure to time it in exactly as it says. It's a special. We've done specially for, well, I know, I requested it, right? He said, so put it in exactly as it says on the timing card. And I thought, it's going to be 4 degrees advance, which is going to be wrong for it. Anyway, we're doing a back-to-back test between this cam and another one. And Terry is doing the testing, Terry Walters. So he calls me up and says, David, the cam says time it in 4 advance. Is that where you want it? And I said, no, that's way up. I said, put it in there. We had an adjustable belt drive on there so we could retime it. I said, put it there and we'll see how much it drops horsepower compared with what it should be. And I think I wasn't even in the country then. I think I was in England. And he dyno tested it 4 degrees advance. And I said, now, with that head, this kind of cam here, and this displacement, it needs to be about 1 degree retarded. So he retarded the cam 5 degrees. Exactly 25 horsepower more and 27 foot-pounds more. It was that big because that cam had exactly the right lobe center line angle for that engine. How do I know? Well, I say exactly. It was so damn close it wouldn't make any difference. It was a 10.5 to 1 motor. If you make 1.4 foot-pounds per cube, then you know from that torque output, your camshaft is optimizing what can be got from a 10.5 to 1 compression. If it's significantly less than that, it's probably the lobe center line angle that's wrong. Well, it turned out that it was a careful build. I used all the best total seal rings and bore finishes and all this stuff. And 10.5, and it gave me about 1.44 foot-pounds per cube. That was very good. So I could say with reasonable certainty that lobe center line angle was on the money. That shows, and I've said this before, and when you've been in it as long as I have, you'll realize it. Those advanced figures on the cam cards are just a good guess. That's all they are. Nothing more. Did I say a good guess? Hopefully they're a good guess. So now we are going to time the cams in peak power on this, are we?
We're doing our best. I've worked on getting the timing set to be able to do that.
Right, good. Because it's my thinking that you can't really do a good cam test if you're going to do a real cam test where you've got to find the ultimate for each grind, where you optimize cam timing, ignition curve timing, mixture and everything. Then it's not a fully operational test. Sure, it is a test of sorts, but it's not an absolute deal. So, you know, what I'd like to see in this test, and I don't want to seem like I'm technically bullying anyone here, but I'd like to see everything set up right, because it will show not only the first cam, what it would do, but also the second, third, and fourth, right? There will be no doubt as to which cam is able to produce the best horsepower, because all other factors have been optimized. Blank spot there.
That was good. Yes,
so what's your thoughts on that?
I really like that, but a big consideration for me is like longevity of this engine, because I have to put my name on it. So is there a way that we decide?
Yeah, we limit the RPM because that's what kills them.
That, yes, sir. But I mean, even like lobe intensity, if this lobe if it rushes on very quickly and it's jamming this valve open and closed over and over.
Yeah, well, will talk to Daniel about that. Who's the other cams?
Brian Salter of Salter Racing.
Right. Has he put his cam in yet?
Yes, sir. So his cam is ground. I don't have it yet, and I don't know the specs on it. I only know we were going around 750 lift. And
What springs have you got on the heads?
Daniel is speccing the springs. We have a set of springs now. I believe they're pack springs, but they're not the end all be all. So we kind of bought springs early. I kind of wanted to wait. So we're looking at buying a different set.
And I think Pack makes these springs, but I know they made some springs for me 5 or 6 years ago for a vintage racing 289 Mustang. It was a single coil spring, and the poundage on the seat and over the nose were lower than a stock spring. Yep.
Wow.
And this cam, which lifted the valves, Ion 600, would turn 8,000 RPM, just like that. Flat tappet cam.
Wow.
Right. Camshaft wear was non-existent, so that was a comp cams. Okay. And was the engine competitive? Oh, sure. It did break the block. It was making so much horsepower. But one of the other guys who was second in the championship said, it's just like chasing a guy with a 100 horsepower nitrous kit. And he was driving the second car in the team. It was the engine that they built against the engine I said, build it this way, and supplied the heads and the cam for. So anyway, did it win anything? No, it broke. And it was just too much. It was over 500 horsepower that was making from 289. That's with stock rockers and iron heads that I ported, because you've got to have period iron heads. Mm-hmm. And a two-plane manifold. I do know there's a guy out there, I don't remember his name, it'll come to me, that does a two-plane manifold for these Mustangs, which was better than the one I had on there, which I'd like to have tried. And it's made, from what I hear from him, as I remember it, it's made from 3 Edelbrock air gap manifolds, bottom, middle, and top. And he cuts them so that they're, I don't know, about an inch higher, but he ports each bit, then somehow makes them so that they can be screwed together so he can match them up. So what you've got is a proper custom built racing two-plane manifold. It would have been interesting to put one of those on, because I know this guy is very finicky about what he does, and his engines are winning a lot of races, or engines with his parts on.
Yes, sir.
So now, what manifold are we using on this?
This is a Mopar M1, so it's the special one that can fit under that flat hood. It's a single plane.
Does it look like the Y and single plane when it's relatively low?
They had a strip dominator or a street dominator sometimes. Those are single planes for Mopars. There was an accelerator at one point. I have one of those, but it has like a raised plenum in the bottom that kind of seems to taper the runners down some.
Have you got it there?
I'll be right back.
Well, while Joe is out finding that intake manifold, we can talk about this, that, or the other. I suspect there may be more to this intake manifold than meets the eye from his description. One of the things that I've found is that, and it could be called a turtle of sorts. Now, that's the thing that Brodex came up with many years ago that goes in the bottom on the floor of the intake manifold. Well, there is this deal with a single plane manifold where one cylinder draws, it's actually in part fighting against the direction of flow that the previous cylinder started. So if you have one cylinder flowing and it's going that way, and one over here flows, this one here is going to try and slow this one down as well as taking air here. It won't take in so much here, but it'll slightly rob that. So you get it right, and you can make it like a hump going across the middle of the runners, and you shape it so that it's curved and curved at the side here, and it has some kind of rise between the dividers, but goes over, so that what can happen is air that's going this way can keep going this way, except any lazy air here can be drawn in to the other cylinder when this one starts to fade in its induction stroke. Now, one of the things I found with this is it'll make the intake runners such that they will produce more low-end torque than they would have done before. In fact, it can make a regular, not high-rise manifold, but a regular a single-plane manifold intended primarily for the street run much more like a two-plane at the bottom and a slightly off pace race manifold at the top. It's well worth trying. Some goop from Goodson. They've got a epoxy that's very robust. Just put some pins in the bottom of the manifold with screw heads on so that it can't, what you put on there can't fall off anywhere, and shape it so that air coming in can turn like this, and from over here it can come down and ride over that hump easier into the manifold. If the manifold that Joe's just going to get has anything like that, then I'm going to suggest it's well worth a try on the dyno, if we get the engine down low enough. We'll see. Anyway, he should be, there you go. He's back.
Right on time.
Right. Okay, show me the plenum. I've just done a section with while you were out talking about what I found on manifolds like that.
I know that's pretty crude. Can you see there?
Yes, and it wants one of my humps in the middle. Right. Right. Let me. I'll send you a sketch as to what it should be like. Right. It looks pretty good. Is this one you've done?
No, Charlie did this one. So there's
Charlie did it. Right. Okay. I should have guessed that was his work. It's all his cuttering work's very good, isn't it?
Yes, sir.
It looks like he's almost machine guided.
Those are the Mopar max wedge ports. So he's port matched as close as he could, without actually having an engine block there. So he said I may need to adjust some of the floor, the roof of the port.
I guess at about this point we need to start calculating out the camshaft. Well, here we have the Vizard Weiss cam program. Those of you who are observant will notice that it says it's for a 24-degree big block Chevy and it's a solid roller application. Now, we're doing a big block Mopar. Fortunately, I found an easy route to change some of the constants to get this program to calculate the lobe centerline angle, the big block Mopar, because the geometry is quite different and the gas transfer across TDC with the parallel valve head versus an incline valve head is substantially different. Anyway, when we get to that difference, I'll let you know. But what we start off with is we enter the bore, 4.36, then the stroke, 4.5, rod center to center length, 7.1, intake valve diameter, a woefully small 2.19, exhaust valve diameter, still way on the small side for such a big engine, but it's a 1.81. Part of the saving grace of this engine that it's got a fairly high compression. And there's an old saying that if you don't fill the cylinder very well, you better squeeze what you've got in there pretty hard. Very sound saying. Now we want peak power at 6,500. Now that I want to stress here that we want the power at 6,500. Now we're going to find that this program will show us what shortcomings we may have to meet our goal. Red numbers in the yellow boxes are the result of a calculation, calculating the data. And I've already taken the liberty of calculating it, but going on down, we put the rocker ratios in 1.6, 1.6, and we want a cam for mid to top end, so we're going to need a dual pattern cam, so we put a 1 in. Then we go across to the calculate data. Boom, hit that button, and it calculates all the data that you will need for a cam selection. Now, let's go across to that column. That's the one to the right of the column we've just entered the data into. And we will see that it's quoting a lobe centerline angle of 106. Well, that would be right for a big block Chevy, but as it happens, for the big block Mopar, it needs to be 3 degrees tighter than that. So our lobe centerline angle, or lobe separation angle, call it what you will, is going to be 103, not 106. Now the 20 thousandths duration intake, 296. The 20 thousandths degree exhaust, 309. Now I know somebody's going to say, well, wouldn't the 50 thousandths number be more applicable? Well, yes, but it's more convenient to calculate the duration at 20 thousandths first. And then you've got the option of deciding how fast to open the valves, and we do that in the next section. Overlap, 90.5 degrees. Advance, 4.6. This is a calculated advance. It's not the almost obligatory 4-degree advance. This actually takes into account the valve sizes and where they need to be in relation to the crankshaft in the opening phase of the valve train. The intake center line is at 4.6 advance, is going to be 101.4. Now, here we come to one of our first problems. Recommended minimum intake valve lift, 988. Recommended minimum exhaust valve lift, 948 thousandths. Well, between you and me, we aren't going to be able to get that. And it wouldn't be any good anyway. It'd be way past the peak flow lift of the head we're using. What we do have is a 750 valve lift limit. So something's got to be done about that. But let's move on. The dynamic compression ratio, 8.5. For a street strip motor, which is what I've chosen here, that's about as low as we want to let it go. We would like to see it nearer 9-1 in this particular instance. Cranking cylinder pressure, PSI, 221, 780 pounds-feet. Estimated power potential, 872. Oh, this does look really good here, but there's a snag. Right below that estimated power, it tells you what the recommended minimum CFM head port flow is. To get that 872 horsepower, we're going to need 426 CFM of flow. We don't have that. We have about 380. So we aren't going to make that 872. Quick calculation here off the top of my head. We're going to be about 100 horsepower shy of that 872. So if we've got everything working well, 772 should be about where we could get to if everything was spot on. That's allowing that we've only got about 380 CFM of flow. Target intake port, CCs. Well, if this is a big block, it would need to be 352 CCs, but it's not. So figure there is redundant for what we're doing. The only thing that I can say is Charlie Savidio has done the heads, and he's one of those head porters that doesn't make the head ports any bigger than they need to be. So we can pretty much assume that the port area for the heads is about right. Next, we come to the intake length in inches. This is from the center of the valve right through to the center of the port where it enters the plenum. I provisionally put in 11.5 there. I don't know what it actually is, but that's what I've entered. The wave reflection, that's the second, third, or fourth wave reflection. The fourth one. Right, now then, we've got all that in. Now we go over and look at what snags we've got. As you can see, the 6,500 RPM limit is giving us a piston speed of 4,875 feet per minute. That's a little bit over our speed limit. I dare say that for brief moments and not too regular use of that 6,500, the parts are good enough to hold everything together. But nonetheless, we ought to look at putting that figure per peak power down slightly. So we'll consider that in a moment. Now, let's go and look at the other factors here. We have the vacuum at idle, which very few other CAM programs ever tell you. In fact, very few actually tell you all this data. Vacuum at idle, assuming it all sealing up properly, 6.7 inches of mercury. Not good. I think what we need to do here is to maybe look at a lower RPM. Instead of quoting peak power at 6,500, let's make it 6,000 and see where we get to there. Well, here we've gone to the 6,000 RPM mark. So let's move along the line here and see what it's changed. After we hit the calculate button, we go across to the next column as we had before, still on 106 lobe centerline angle, but the cam duration has dropped, 287, 297. And you can see as we go down the list, things have perked up in the civility area. We're now calling for 925 lift and 888, so it's a bit less. We have 9.6 for our vacuum, and if we go on across the page, we've now got a dynamic compression ratio of 8.8. The next subject on the list is the cranking pressure. Now this is 234 psi. That's getting a bit high for 93 octane fuel, and my guess is that it will probably, but not certainly, need an octane booster. Now that will all depend on how good our mixture atomization is and what the mixture ratio is, etc. A lot of things. Maybe just about doable, but my guess is probably not so much. Anyway, let's go on down the list. Horsepower and torque. Look at this. 783 foot-pounds. We've actually gone up a couple of foot-pounds on torque. However, our expected horsepower has dropped by, about 50 horsepower at 818. Now, those figures are nice, but let's have a look at our required CFM of port flow. 401 CFM, still higher than we've got. But dare we put anything in that's less duration than this, because our cranking pressure will go up sky high. So let's see what we should do here. Let's stick at the 401 CFM requirement, even though we've only got about 380. Now, induction length, in this instance, we go to 12.3 inches in length for the intake. With the fourth reflection, that will give us peak horsepower RPM of 6,016. Well, that's close enough to 6,000. And our torque will be about 4,700 RPM peak. So fairly good numbers. That's where we would kind of expect it. At this point, we know what we want in the way of a camshaft for this engine. That's all very well. If we go across the board here, we find that cam industry as a whole probably has close to 1,000 different solid roller grinds for a big block Mopar. So, how long is it going to take us to go through all those to find the optimum? Close to forever. Fortunately, we have a way out here. If we go across the screen now, down to the bottom left-hand corner, we see a button labeled Update Excel. This is where Excel really saves our butt. This has a spreadsheet with so many cams on it, it will boggle your mind. And it's not just a list of cams. Let me show you what it contains. We'll go to that sheet now. Well, when we hit that Update Excel, we get this. Hundreds and hundreds of cams. Let me just start going up the page and you'll realize just how many cams there are out there. And this is not a complete list. I've kind of ignored some cam grinders because I know they don't do good profiles. But you can see it goes on and on and on and on and on. By using one of Excel's facilities, we can sort these cams out to find from this 4-figure number of cams possible to find the nearest one to what you're looking for in under 90 seconds. It's near a minute, but some people might be a bit slow. Under 90 seconds, guaranteed. But here's the problem. We've got 2 cams we'd like to try. We can either pick the big duration one and try that, the smaller duration one and try that, or something between. Well, to be honest here, Joe, I think I've got the perfect solution for this dilemma. It's a question of, do we grind the big cam or the smaller one, or one between? Any one of those 3 solutions could always leave us in doubt. So here's what we do. We ask Daniel for 2 cams. What a nerve. Anyway, so that's what we'll do. We'll see if he's good to go on that. I have a suspicion he will want to learn from this as much as we do, so I think we'll be all right. So that's the solution to the problem. 2 cams of the specs we've just worked out. As you can see, these cams only differ in the duration. Not much in it, but that may make the difference to a much more drivable motor that is actually operating near the range of the heads rather than one that is obviously way past that. Now, I'm not saying that the big cam won't make a little more horsepower, but the shorter cam will definitely make better torque, especially lower down, and be more drivable. And I don't expect it to be that much short on power, but we'll see. Anyway, with all that said, let me just hand you back over to Joe for the conclusion of what I hope is a captivating cam program. You may wonder what that title was all about. I am sure you've heard the expression, starting with the best laid plans of men and mice. Well, we're subject to that. Now, let me tell you, at this point in time, Daniel, myself, Joe, are aware, or have been made aware, probably via Charlie, that we cannot put bigger valves in this head. Why? This is straight from Charlie. 1, the chamber walls are as thin as Charlie reckons they can be and survive. So, putting in a bigger valve means taking more off the wall, the large wall adjacent to the spark plug. Won't live. Secondly, he's saying that the short side turn is overtaxed anyway, and putting in a bigger valve will make it more overtaxed, and the speed across the top will be too much, and flow is unlikely to go up. Well, the first one eliminates putting in a bigger valve straight away, so we're stuck. So at this point in time, we have to consider what we're going to do with these heads. And here's the crying shame here. I've looked at the figures on these heads, the flow figures, and most importantly, the port energy figures, which have a lot to do with how well the heads work. Charlie has done a fine set of ports. The port energy he's showing on there, the highest port energy figures I have seen on a pushrod head, and are marching in to the territory that I've seen on Formula One heads. And we're going to have these heads fitted on a long block that is a total mismatch. What options have we got? Well, it needs somebody to, my idea. I haven't talked to Mopar Joe about this yet. I'm kind of disappointed that we can't go ahead as planned, or if we do, we're not going to get what we want. So, this is what I think we should do. We should sell these heads that Charlie's modified, and let me tell you something. The porting job on them, from the numbers, is nothing short of brilliant. If you've got a big block Mopar engine that's around the 427-inch mark, these heads are going to be awesome. Awesome. What we need to do is to get some heads that we can install maybe slightly bigger valves. And I'm thinking, from what I remember what Charlie said, that there's a head out there that's 2.25 intake. I'm sure we could get that to 2.3. That might solve our problem. But here's the thing. What I've done here is that I've, how shall I say, discussed this with my partner in crime here, Mopar Joe, to see and explain to people what they could do if this situation was insoluble as far as a cure by different heads. And I can tell you now, we won't get to what we want, but we can approach it a lot closer. I'm going to do a part 2 of this, which will explain how we can cut the gap between what we can get and what the engine actually wants. I stress that, what the engine actually wants, not what we want. It's got nothing to do with what we want, it's what the engine wants. So, until part 2, I'm going to say, guys, hang on. We are going to, the team, that is Daniel, Joe, and I, and Charlie, are going to see what can be done, how we're going to do it, etc. in the next episode, which should come up very soon. So hang in there, and thank you very much for watching.